Hello, my name's Derek Gorley, and this is a recap of a presentation given at the University of British Columbia as part of my ECE 412 Introduction to Computer Security course curriculum. The topic of this presentation will be a security analysis of the iClicker audience response system, conducted by myself and 3 fellow colleagues. Here's a brief outline of this presentation. I'm going to present an explanation of how the iClicker audience response system works, outline the goals of this project, bring to attention some of the related projects we were able to find, describe our approach to this security analysis, highlight some of the vulnerabilities found, and present possible solutions to these vulnerabilities. The iClicker audience response system consists of a base station and iClicker remotes. Remotes communicate with the base station using RF frequencies in the 900 MHz spectrum. Students can answer clicker questions posed to them by course instructors using their remotes. The clicker IDs and answers for students are stored upon a computer connected to the base station by course instructors, which allows them to access these answers anytime in the future. The main goals of this project was to see what we could develop to skew the results of a voting session or simply mess with iClicker voting sessions. And more specifically, what could be done to prevent this. So before starting our project, we decided to scour the internet and see what sort of related projects we were able to find. As shown in the first picture here, we were able to find a few instances of reverse engineering other 900 MHz RF clickers. However, they differed from the iClicker considerably, as of course, the code base installed upon the clicker was nowhere near that of the iClicker from what we could see from our preliminary studies. So, we were able to find one instance of an individual reverse engineering or attempting to reverse engineer the iClicker as shown in the second picture here. He claimed he was able to get his clicker to rotate through a various set of IDs. However, he only provided pseudocode snippets and no actual working examples, so we weren't sure if his claims were legitimate or not. So we decided to start from scratch, and we came up with 2 main vectors of attack. The first was to attempt to decode and intercept wireless communications between the iClicker remotes and the base stations, and perhaps attempt some sort of a man-in-the-middle attack. The second approach was to possibly alter how an iClicker communicates with the base station by altering the software that runs upon an iClicker, and see if we could develop something and do something with that. So starting with the first vector of attack. From a wireless standpoint, it's important to note the iClicker operates on the 915 MHz RF spectrum. iClicker says this is to avoid any interference with Wi-Fi technologies that are often installed in schools that operate on the 2.4 GHz spectrum. However, many of you know that when you connect your iClicker to a base station, you have to first pair it to a channel the base station is running upon. iClicker says that 2 base stations can be in close proximity on separate channels, say AA or AB, and not interfere with each other. Our intuition gave us a good feeling that these channels, AA and AB, probably meant the frequency that the base station was running upon. So the first task was to determine what were these frequencies. Well, luckily, FCC reports are your friend. Thankfully, consumer wireless devices have to undergo testing by the FCC, and these reports are made publicly available. First off, they are full of all kinds of cool pictures of their test setups, like this one here of an iClicker on a tabletop in an anechoic chamber. But more importantly was the actual frequency of every single channel the iClicker operates upon. So, an important part of being able to reverse engineer the RF communications was knowing the protocol used to communicate between base stations and clickers. Luckily, the iClicker said on their website that iClicker and iGrader software are both open source. So at the start of the semester, we sent a polite email to iClicker saying, we meet all your criteria, can we please have a copy of your source code? Well, let's just say about 3 months later, all we managed to get was a compiled DLL file and a 2-page Word document describing their API. And conveniently now, the iClicker website says they only offer a common API. Go figure. So we gave up on our first man-in-the-middle attack by intercepting wireless communications and decide to see what can we do with the iClicker remotes themselves. And we started that by disassembling the iClicker. Now there's 4 major points on an iClicker remote that are worth noting. The first is the ATmega8 microprocessor in the bottom right corner, as you can see here. It is connected via an SPI bus to an RF module manufactured by Siemens in the top right corner, as you see here. Third is the AVR in-system programming port, or ISP port, was exposed via the PCB in 6 pads. This allows us to read from and reflash the ATmega processor without removing it, a major godsend. And finally, a neat little fact is, there's a backup clicker ID pasted to your PCB. Many students complain that their iClicker remote IDs rub off the back of the casings of the remote. Well, if you take apart your remote case, there is an extra clicker ID pasted to your PCB. So the first step we took was to solder some header pins to the ISP port. This made it easier for us to attach and remove our programming device, the AVR-ISP Programmer, as shown in this picture here. The first thing we tried to do was dump the EEPROM memory contents to file. We had a good feeling that a clicker's ID must be stored in the EEPROM memory. This, shown here, is the memory contents for the EEPROM of a clicker with the ID 0D92FC63. And as you'll notice, this ID is stored in the very first line of memory. Well, at least a portion of it is. The first 3 bytes are. What about the 4th byte? Well, you might notice that if you XOR the first 3 bytes together, you in fact get the 4th byte. And this is true for all iClicker remote IDs. So, now that we knew where the clicker's ID was stored in EEPROM, and we knew the fact that we could change it by reflashing the EEPROM memory contents with our programmer, we could do all kinds of things. For instance, it made it trivial to clone a given remote. Say you had an instructor's remote ID. We could make an exact replica of his remote by just simply writing his remote ID to our EEPROM memory contents. This would allow one to, say, hijack control of clicker question sessions or even PowerPoint presentations, as some instructors do in fact use their iClicker remote as PowerPoint controllers. So we decided to delve further into the iClicker software upon the remote and see what we could do. Since we were constantly reading and reflashing our remote, we quickly became frustrated with the simple fact that the buttons were on one side of the remote and the ISP port upon the other. And there was also the big problem that when you take apart the iClicker remote case, the batteries love to pop out at the most inopportune moments, cutting the power to the whole circuit. So we built this, our iClicker development platform. It's simply the PCB of an iClicker remote with external buttons attached to it for easy access. We also added a small voltage regulator so that we could use a 9-volt battery to power the whole circuit. Now, we knew how to play with the memory contents in the EEPROM. We decided to look at the program memory contents as well. We dumped the contents of program memory to file, and we decompiled this into hex. We decompiled this hex into assembly. The result was approximately 2,000 lines of assembly code. Yay! Now we had to figure out what on earth do we do with 2,000 lines of push, pop, loads, and stores, and so on. So, we pulled out the trusty datasheet for the ATmega8 microprocessor and started searching for what we thought would be important special function registers. By looking at the PCB and testing it with a multimeter, we were able to determine that the clicker buttons were attached to pin C of the microchip, and the datasheet told us that pin C corresponds to memory address 13 in program memory. The next important address was determining where in the code the EEPROM was read to read the stored clicker ID, and this mapped to memory address 1D. So with these in mind, we dived into our assembly code and started searching for these special memory addresses, and this is what we found. This first line of code tells us the point at which button presses of the remote are read into memory. And this snippet here tells us when the EEPROM is read to get a clicker's ID. These are the two main points of code we needed to know. By patching these code segments, we could do all sorts of things. Patching the code was followed by replacing a given instruction with a call to an empty segment of program memory. By jumping to an empty segment in program memory, we could inject any kind of code we wanted, as shown here. Now, a point worth noting is that the disassembler we used that came with AVR Studio used PC relative addressing. This meant that anytime we replaced a line of code with a call to another segment, we had to ensure that the size of the instruction used matched the one that we were replacing, as to not mess up the code space and shift down the whole addressing. This was sort of annoying, but we were able to get around it. So now that we were able to patch the code and knew the location of all the special function registers, we were able to do all sorts of things. In fact, the first thing we did was develop a rapid-fire iClicker remote, in which every time you pressed a button, the iClicker remote would randomly change its ID and send a new ID to the base station, allowing you to promote any answer you wanted. A video of this is available upon my website, derekgorley.com, if you would like to see it in action. So a point worth noting is as we played with the iClicker, we noted that the ID sent over the airwaves is not in fact your 4-byte ID. In fact, it goes through some sort of ID obfuscation routine as shown in this picture here, and only the first 3 bytes are sent over the airs. So, from a security standpoint, what we decide to mess with is the integrity of iClicker voting sessions. So, here's a plausible scenario. Suppose a professor poses an iClicker voting session that says, when should our review session be? And, unfortunately, all of your classmates choose at Wednesday at 8 a.m. and you in fact want Friday at 1 p.m. because you're just not a morning person. Well, given our hacked iClicker that could randomly let you promote any answer, you could mess up the whole integrity of this voting session by sending fake answers or fake responses to vote for E, Friday at 1 p.m. And as you can see, in fact, here, over 100 fake responses were generated, and the session would be held at Friday at 1 p.m. if the instructor didn't notice errors in this voting session. So how could all of this be prevented? Well, one of the most important security principles is to layer your defenses. There are two main things that iClicker could have done that would have prevented all of this. The first is lock bits and fuses. There is a bit on the Atmega microprocessor you can set that will prevent the dumping of EEPROM and program memory contents to file. Without the ability to do this, we probably wouldn't have been able to do this project as easily as we did. Another possible way to prevent ID or fake ID generation like we did would be to do ID authentication. If student answers were compared against a content management system such as Moodle, a teacher could easily find which clicker IDs are registered to students in this course and which are bogus IDs that were just generated by a hacked iClicker. So, in summary, we went over some of the problems that the iClicker had. We were able to spoof any clicker ID by modifying EEPROM memory contents, and we're also able to generate clicker IDs on the fly to promote any answer we wanted. Some of the solutions we came up with were to simply set the lock bits on the iClicker remotes and to use an ID authentication scheme. We also compared this to other projects, and in our course, we actually presented a working demo, but as mentioned before, you can see this on my website or on YouTube. We were able to add rapid-fire functionality to our remote. We also deciphered how clicker IDs were obfuscated and presented a diagram of this. And we finished our presentation with questions, answering questions that any students had for our project. Thank you very much for watching this presentation. Again, my name's Derek Gorley, and you can read more about this project at my personal website, www.derekgorley, gourlay.com.